Okay, let's start. Did you guys figure out the tank problem?
What?
The tank problem.
Triangle, similar, right?
Yeah, that was one way to do it. The tank problem, this guy.
Oh. Baseball plus baseball.
Huh?
Similar triangles, obviously.
Yeah, I did similar
That was
triangles.
one way to do it, yeah.
Do you get like
you could
X
have
plus?
put this guy here,
Yeah.
because this is two triangles. You already know this distance.
It's
and
4,
here
right?
you use similar
Yeah.
triangles.
What's up? Alright, relax. What's up?
What's the other way?
Well, put it on the XY axis, which I mentioned before. Find the equation of this line.
Oh,
Is that the other way?
but we don't know
That's
the
another
point.
way, yeah.
Yeah, because you have the bodies, right? Yeah.
And you just use the equation of the line to find the width.
Do you make the integrals that ugly on purpose or something?
For like problem 1?
Yeah,
Yeah,
they're.
that was kind of ugly, yeah. My goal is to make the final feel super easy. It's like the only chance some of you have.
Wait, so what if we did that wrong?
What?
What if we did do similar triangles or
25 points.
I don't care which way you did, as long as it's right.
Yeah, I'm gonna lose some points on that.
As long as it's mathematically sound, then you did the right.
25 points.
This is going to take a short look at polar coordinates. We'll definitely finish this next on Thursday because we won't have enough time.
I like.
By the way, what problem did you guys do first?
No, I didn't compute it out.
The first one.
I got a fraction.
That's 25 points right there.
Yeah, 50.
What problem was the easiest one?
The first one.
The tank one was easier compared to the, for me. Finding the washer, I know it's like
mad easy. It was like
2 pi RH and R is this minus that and all that shit, but the limits are kind of messed up, I guess.
Whatever. It's just my future.
It's my feature.
What? Not really. That's minimum points. Anyway, let's talk about what these are. We'll do more on this. We actually covered a little bit of this before. All right, can talk about that afterwards. We spoke a little bit about this last time when we were talking about parametrics, but it's a new coordinate system. New way to look at the XY plane, because X and Y is just sometimes not good enough. Right? It's based in terms of, there are two things that you worry about. The angle theta is what we usually denote it, made with the positive x-axis. And the distance from the origin, which we usually call r, which can be thought of as the radius of a circle. So basically what I'm saying is you have a random point here. Now what we call the xy coordinates, like if we find this point, you can take an x value and some y value, and that locates the point. This sort of setup, you'll see, creates a rectangular kind of system for locating a point. This is called rectangular coordinates. It's just a coordinate system that you're used to. Tell me the x coordinate, tell me the y coordinate, and I can figure out the location of the point. This is called the rectangular coordinate system. In the polar coordinate system, that same point will be located in a different way. Right? So here I have the x-axis, the y-axis. Here's my point. But now I don't think of it in terms of x and y. I think of it as a distance from the origin, which I call r, and an angle that it makes with the positive x-axis. Right? So if you give me an angle and a distance, I can locate the point that way. Right? And I sort of think of it as this is sort of on the radius of some circle. Right? It's really a coordinate system that depends a lot about circles and basically how the trig ratios were developed. Right? That does a lot to sort of give you some intuition about it. So we're going to do a lot of things with polar coordinates here. In section 9.3, we're going to do a lot with polar coordinates. You won't fully appreciate it until you get to calculus 3. So we're going to do a lot of stuff and you're going to like, okay, yeah, that's cool, we can do all this neat stuff, but it's really in Calc 3 where you see the applications of this. It's really going to make your lives easier when you get to Calc 3. You're doing these crazy integrals. Sometimes thinking of it in polar coordinates can make your life a lot easier, right? So it's just a different way to locate a point. You don't talk in x and y, you talk in terms of angles and distances, right? So you locate a point that way. Some equations are immediate. Right? I mean, you think of this in terms of how you set up a trig. You can sort of imagine some right triangle being made here. And so I can look at two sets of formulas. The first set I can think of as something like, what would the x-coordinate of this point be if I was to represent it in terms of r and theta?
R cosine theta.
R cosine theta, right? So here my x would be r cosine theta, right? Because cosine is adjacent over hypotenuse, so the cosine of theta is the adjacent, which this distance here would be the x distance. This distance here would be the y distance. Cosine of theta is adjacent over hypotenuse. Sine of theta is opposite over hypotenuse from SOHCAHTOA. And so we know that your y value will be given by r sine theta. Right? There's another set of formulas. Sort of doing the opposite. How would I represent r?
R squared equals x squared.
R squared equals x squared plus y squared is one way we can do it using the Pythagorean identities. How would I represent theta? Think of this as several ways. I can think of this as the tan inverse of y over x, or I can think of this as something like the sine inverse of x. How would I think of this in terms of sine? Or
Y
cosine?
over R.
What?
Sine inverse Y over R.
Sine inverse of y over r. Right, which the r I can write in terms of x and y's here, or I can think of this as the cosine inverse of x over r, right? Which again I can think of this in terms of the radical of x squared plus y squared, plus or minus, right? So those are two sets of forms that we can get just by thinking of this in terms of SOHCAHTOA and trig. These forms are super important to remember. The problem with tan is, this is usually how they define it, but tangent has problems somewhere, obviously. It's not defined everywhere. So if this angle here happens to be pi over 2, everything gets messed up. But the sine and cosines will always give you an answer. Right? But I just wanted to mention that. So, note. In rectangular coordinates, something like the location of a point, location xy of a point is unique, right? But you give me an x and a y, there's only one point with that x and y coordinate. In polar, this is not true, though. Polar coordinates. This is not the case, right? Because angles can repeat, right? You can have terminal angles all terminating at the same point. So, for example, if I take a coordinate in r and theta, it's actually going to be the same as me saying r and theta plus 2 pi, right? Every 2 pi I'll get the same point, right? So every 2k pi, where k is an integer, if I add or subtract that from my angle, I get the same point. So there are like an infinite number of ways to represent any given point. All you have to do is vary the angle. One strange fact about R. So I told you it's a distance, but you can think of it as a net distance sometimes. We can sometimes think of it as negative. We deal with this by flipping the angles. And this is mathematically consistent based on the equations that I gave you over here, so it's not something you really have to worry about. But let me just show you what I'm talking about. If I have a point r theta, right, which I'm thinking of as being this point, this is my r, that's my theta. It's equivalent to here's my point over here. This is theta, this is r. As if I reflected this 180 degrees and think of this here as minus r, right? However, now I think of this angle, theta plus pi, right? So if I travel 180 and sort of flip back, I get to that point. Whenever I can be in that situation, and all that means is just I think of r as being in the negative. Like my distance doesn't measure towards the point, it measures away from the point. You can think of it as telling you a different direction. Right? So that's one thing that might be a little strange. Just wanted to mention that. Okay, what else did I need to mention? So yeah, I told you how it's set up. Maybe I can actually give you some concrete numbers. I want to get to the polar graphs, but I don't think we will. Those are pretty cool. We'll do it next time, though. Concrete example. What if we consider the point r theta equals 2 comma pi over 4? Right, so I'm thinking of this in terms of polar coordinates. How would I plot that? What would that look like?
The Pac-Man. The Pac-Man too. Or I mean,
The Pac-Man?
We elevate like pi 4 and then you just walk.
Well, you
to-
start measuring the angle from the positive x-axis, pi over 4,
and just walk 2.
and then from the origin, you shoot out a distance 2,
Yeah.
right? That's this point here.
doesn't that look like a Pac-Man to you?
Well, I guess if you put the rest of the head on.
Yeah.
Is that what you mean?
They always look like a
Yeah, so another way to think of that point, though, is to think of it as the point. Another way to get to this point is to get to exactly the opposite point in the exact same distance, right? So if I wanted to think of it that way, I could actually write this point as minus 2, and what would the angle be?
pi over 4 plus pi.
Right, it would be 5 pi over 4. Right? Because of the way, again, I can think of this in terms of a circle. Remember, pi over 4 means 1, 2, 3, 4, 5 pi over 4s. Right? So this point is actually equivalent to that point, right? You can think of it as just a flip, right? Because if the r is negative, it means you move away from the point instead of towards the point.
But how are they equivalent? The points are not in the same spot. Aren't they like in the opposite corners? They're not in the same spot. How are they
That's why
equivalent?
the angle is different.
Yeah.
Because then you swing back around.
Yes, that's the angle would change to account for that. The idea is because we know that r squared is equal to x squared plus y squared.
Yeah, draw it.
Remember, your r can be plus or minus the radical.
Right.
Right? So there's a case where you take a positive radical and things work out the obvious way. The case of the negative radical, it works out this way, which you can actually tell. If you use those sine and cosine equations here, you'll get negatives in the angle, and you use coterminal angles to figure them out, basically. So
I feel like he's still doing
I want to move on to the points, so
and then you back
I won't
up.
belabor the point right now, but you can think of it in terms of these equations that I have written here in terms of sine and cosine. If you realize the x and y coordinates, you'll get them if you use these values for r and theta, you'll get the same points if you use these values for r and theta. And it's just because of how sine and cosine deal with these two. Right? The sine of this would be negative, and the cosine of this would be negative. And so when you take r times cosine, the r is negative and the cosine is negative, so the multiplication gives you a positive, and that's why you end up there. Right? So, that's there, I'll tell you. Okay, those are some technicalities. Let's do some conversions, and then some very simple sketches, and I guess next time we'll do some more complicated and nice sketches, like what was on the bonus problem.
Did anyone try it?
Talk about sketching polar curves. Some simple ones first. Let's say I told you the curve, I give you the equation r equals 1. R equals 1. How would you sketch that curve in polar coordinates? What curve would that be? It will literally be a circle of radius 1. Right? Remember how we're thinking of r, right? R is what? The distance from the origin. So me writing down r equals 1 is saying these are the set of all points whose distance from the origin is 1. This ends up being just the unit circle, right? Now, what is the equation of this in rectangular coordinates? Well, x squared plus y squared equals 1, right?
Yeah.
Hopefully you can already appreciate how simple this can make certain things, in particular circles. Here's the equation of a circle in xy coordinates. It's not even a function. Fails the vertical line test. In polar coordinates, it's a constant function. And it's actually a function. This will pass the vertical line test if we're in the r theta universe, right? So going from this to that, where if I want to solve for functions, I'd have to deal with radicals. Whereas here, I would never have to deal with a radical. It's pretty easy to, I wouldn't need it, right? So think of all those integrations that I was giving you back when you had things like this, and then you might have needed a trig sub and blah, blah, blah. If you switch to polar, you're working with a constant, right? So that makes things sort of nice. Let's look at another kind of curve. Here's an equation. Theta equals pi over 4. What would that look like? What kind of curve is that?
What was the question?
Sketch the curve. What kind of curve is that? It's a line, right? Remember what theta is, the angle you make with a positive x-axis. So if I make an angle of pi over 4, what are the set of all points that for any r value will be at that angle? It's just going to be a line. Right? So this is a straight line. In fact, this is the equation of the line y equals x. Right? So here I have a non-constant function. Slope is 1. Turns out to be a constant function if I think of it in terms of polar coordinates. Right? So in the r theta realm, this is just a horizontal line, whereas here it's a line with slope 1. Let's look at something else. Let's get a little bit more complicated. What does this function look like? R equals secant theta. That's right, secant is 1 over cosine. How do I use that to help?
So 1 over 0 would be, does not exist.
And 1 over 0 doesn't.
No, like theta being 0 does not exist.
Where do I go from here? What do I do?
Yeah, different values of theta, and then like for each value of
Yeah.
theta.
Think simpler. Think in terms of equations.
R cosine equals 1.
R cosine theta equals 1. What's R cosine?
Something.
That's just x. This is simply the line x equals 1. Which is why you sort of said, oh, that's undefined. It's because it's a line of undefined slope.
Oh.
This is the line x equals 1. That's the equation of the line, right? So it's not always easier, right? But it's usually very much easier when you're dealing with circles or circular, anything that has sort of sums of squares. You can really simplify using polar coordinates. So yeah, this is what the equation of the line x equals 1 would look like. Let's do something slightly worse. R equals 2 cosine theta. What's that curve?
Oh, I saw this. It's a circle, I think.
It is a circle.
Yeah.
How do you think of it? How did you figure out it's a circle?
Yeah.
With the origin 0, 1. I think.
No, why would it jump origin?
Nah.
Maybe, but I don't know.
I'm pretty sure origin is 0, 1. Radius is a 1.
Wait, if theta is 0, then R is
I don't know. It's funny.
0. So
Well, how did you come up by that?
Homework. I mean, the textbook.
sure.
I'm correct
Yep.
though.
You know x equals r cosine theta,
Yeah.
just like in general, so you can solve for cosine theta there and then replace it. And then,
Yeah, so one way I can do this, method 1,
and that's how the textbook did it.
is to just, I can multiply both sides by r. I get r squared equals 2r cosine theta.
And then R cosine.
Right? What's r squared? X squared plus y squared. And what's r cosine theta? Well, that's just x.
Yeah.
Which means I have x squared minus 2x plus y squared equals 0. Complete the square here. I get x minus 1 all squared plus y squared equals 1. So basically this becomes
never mind. It's 1.
a circle centered at 0, 1 with radius 1. Alright, so it's an off-centered circle.
Perks of reading ahead.
There's another way I could figure out what this is.
Still got it wrong.
What? Nah, yo.
A method I'm going to show you and that we're never going to use again. Plot points, because you know this is too elementary. I can really just plot a bunch of points, right?
Yeah, that's what I
So
was thinking, actually. And you could go
let's look at how my theta is behaving. It could be something like 0,
pi over.
pi over 2, pi, 3 pi over 2, 2 pi. Those are the basic points.
But it'll be 2.
We'll see why this method is a bad method to choose, especially in polar coordinates pretty soon. But let's say your theta is 0. What's your r?
0.
No, 2 cosine theta. Theta equals 0. Cosine of 0 is
1.
1, so r would be 2. What is pi over 2?
Cosine of pi over 2.
0. What if you're at pi?
Negative 2.
What if you're at 3 pi over 2?
What's the phase difference? 0.
2 pi. You're again at 2. So you can literally go and you can plot these points, right? Based on your knowledge of polar coordinates. So you can do here. And so you know, here's where theta equals 0. Here's where theta equals pi over 2. Here's where theta equals pi. Here's where theta equals 3 pi over 2. Right? So when you're on the angle 0, your distance from the origin is 2. So you're at this point here, 2. Right? When you're at pi over 2 on this line, your distance from the origin is 0. Of course, cosine is just looping in between that. That's going to give you that curve. To move from here, you're always moving counterclockwise to hit the next point. When you get to pi, right? If you're going towards pi, what's the distance?
-2.
-2.
Comes
But what
back.
does the negative mean?
Comes back
You
again.
flip back. You reverse the distance, right?
You just
And
make
then-
it work.
Now, if you're 2 pi, that puts you back here, right? So you end up drawing it that way. This little exercise we just did is very important. We're going to beat it with a stick next time, right? Because that's going to help us do more complicated curves. So plotting points is one. I guess I can mention this in general. It turns out things get a lot more complicated if I like multiply this angle by something like a 3 theta.
Then like both
That would
of
be
them.
a lot. Very different. Let's say that. Don't want to say harder. Well, maybe it's a little harder.
Okay. Wait. Jhevon,
Yeah, the whole.
can you show us what the graph looks like from the bonus?
Yeah, but I haven't taught you that yet.
Oh. Yeah. Just a simple shape. Just
This
draw
one
it
is
out.
Very simple.
Yeah. Just
flowery
yeah.
petal thing.
Flowery petal. Yeah.
Yeah.
I don't know. Let's see.
SO petal.
What did I ask? Sine 3 theta. Let's
Yeah.
do that one.
Yeah, that's what he given the point.
Yeah.
We don't even know this.
So I wouldn't have plotted points because you need to plot a heck of a lot more than
Yeah.
that to figure out
That's
it
what I
looks
tried to do.
I
The
gave up.
trick is to actually graph that function first.
Oh yeah.
So if you graph r versus theta, what does sine 3 theta look like?
Just
A
not-
big graph.
Between 0 to 2 pi,
Frequency. The,
Yeah.
this
frequency.
3 tells you how many times it's repeated,
Frequency,
right?
yeah.
We're going to talk about that more next time. In my trigger view, didn't I do how to graph these guys in general? Amplitude, phase shift,
Yeah,
all that
yeah.
stuff? Yeah, you're going to need to
Yeah.
remember that for
Okay.
this section. So by Thursday, you need to remember
You should have
that.
said
So
that.
basically what you're going to happen is you're going to have 3 sine functions being done in 2 pi, right? Remember each sine will
Yes.
have 4 sections.
Yes, you did.
Oh God.
Yeah, that's.
So, and then here's going to have 4 sections.
It was beautiful. Yeah.
Here's going to have 4 sections. In each section, you're going to have a sine. So it goes from the middle to the top, to the middle, to the bottom, to
Yeah.
the middle, to the top, to the middle, to the bottom, to the middle, to the top, to the middle, to the bottom.
Understand to the bonus.
So you're going to start with this, right? And from this, you're going to graph what the polar curve looks like. So basically, you're going to figure out all these angles. What are these angles? When you hit maximums, minimums, or zeros are important points, right? So this is a 0. What would this be? Well, I took 2 pi. I divided into how many sections? It was 12.
3. Oh,
Right? There were 3 sections where
and then
4.
4, right? Yeah, 12. Yeah.
Right? So 2 pi over 12. This is pi over 6. Right? This would be 2 pi over 6. Right? 3 pi over 6.
4 bars. Okay.
4 pi over 6.
Yeah.
5 pi over 6.
Okay.
6 pi over 6. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. And 2 pi. Right? Now, basically what we're going to do is, and the height would be 1, right?
Uh-huh.
So here's how you graph it. You think of the r, you think of it as being on a circle, again. So I'm thinking of, this is a set of all points that is the distance 1 from the origin. Those are my r values. Draw this very faintly because it's not a part of the graph. Right? So I'm at a distance 1 from the origin. Then I'm going to draw in all my important angles. So obviously the pi over 6s are pretty important. So I'm going to do the pi over 6s. So those angles here. Notice that I split 2 pi into 12 sections. My circle is going to be split into 12 equal slices. Right? So here's going to be my pi over 6, my 2 pi over 6, my 3 pi over 6, which is pi over 2, my 4 pi over 6, my 5 pi over 6, my 6 pi over 6, which is pi, 7 pi over 6, 8 pi over 6, 9 pi over 6, which is 3 pi over 2, 10 pi over 6, 11 pi over 6, and 2 pi. So now here comes the fun part. Here we're going to finish. Now when I'm at, the angle is 0, what's my distance from the origin? 0.
0.
So you start at 0.
Okay.
When I hit the angle pi over 6, what's my distance from the origin? 1. So I move from 0 and I jump to the circle of radius.
Why is it circular?
Why do you?
Why is it curvy? Why is it not
Yeah.
straight?
Because it's a sine, right? My
Oh.
distance is gradually increasing,
We're just like,
right? Now when I come back to 2 pi over 6,
Oh.
where am I?
that's
Back
like-
at 0. So I'm going to loop back here. That
Oh.
creates one loop.
Easy. I mean,
Right? Now I go to 3 pi over 6, which is here,
-1.
but it's minus. What does the minus mean? Instead of going towards 3 pi over 6, I go backwards. I go down.
Oh.
Okay, now you lost me.
We'll do it a lot more on Thursday. Because the negative radius means you go in the opposite direction. That's what it
alright.
means. Then when I go back to 4 pi over 6,
go back.
Go back to the origin. 5 pi over 6, I go back to the circle of radius 1.
Yeah.
Oh, you got it right.
You got
Pi,
it right.
come back to 0.
Well, this is
7 pi over 6 is here, but my radius is negative.
negative.
So I don't go towards 7 pi over 6, I go back. Basically, I'm going to retrace this loop.
Oh, alright.
And then I'm going to retrace that loop for the rest of it. So it was actually a 3-petal thing. So that's the graph here.
I see.
It's beautiful.
We're going to talk much more about it on Thursday. That would be the graph.
So the graph of cosine,
Cosine would
3 theta would be
like the opposite.
Cosine 3 theta would be this rotated. The pedal would be on the axis.
I think
Okay, see you guys Thursday.